All right, guys, Mr. Jenkins here. All right, guys, Mr. Jenkins here with really the last lesson of Chapter 5 that we're going to be covering. I may give you just the notes on 5.7 just so you can look at it, maybe have a bonus question, but for all intents and purposes, this kind of wraps up the main part of the instruction for Chapter 5. So after this lesson, we'll kind of start to study. The plan for right now is to introduce the study guide to you guys on Thursday, question and answer on Friday, and then probably test on Monday. Okay, that's the plan for now. Anyways, let's go ahead and get to it. So looking at A, and so our lesson is about the fundamental theorem of algebra. So we'll look at that here in just a second. We've already talked about it some, so we'll just expand on that conversation. It says the blank of a polynomial tells you how many roots, real or complex, the polynomial has total. That would be the degree. We look at the degree to tell us that. All right, so a second degree polynomial or a quadratic has two solutions, and so on and so forth. That's kind of the main part of the lesson. A real zero, rational or irrational, shows up as an x-intercept on the graph, right? It's the value of y where x equals 0. All right, so some examples using quadratics, what we're most familiar with. Two real zeros would have two x-intercepts. So this particular graph would tell us that, since it goes through 2, 0, and negative 2, 0, that we would say x equals plus or minus 2. Okay. This one has one real zero, all right, at 1, 0. But this is a good thing to know too. That would be one of those with the multiplicity of 2 when it bends on your x-intercept. And then when you have that void under the turning point or over the turning point, then there are no real zeros, which we now say this would have two complex solutions or roots. All right, so that gets us to the fundamental theorem of algebra. Says if p of x, so any kind of function rule, is a polynomial of degree greater than 1, then p of x equals 0 has exactly n roots, including multiple and complex roots. All right, so basically what that says is that the number of roots depends on the degree. Okay, so kind of just getting to that, how many roots does this equation have? It says, I know it's tough to see, but it says 12x to the 5th plus 3x squared minus 17x to the 10th. That's not written in standard form. On the notes, I write it in standard form, but just to save time here, what we care about is that x to the 10th. So this is a 10th degree polynomial. So this would have 10 roots. All right, so that's basically it. That's the fundamental theorem of algebra, which, like I said, we've talked about that. Okay, so example 2, which will take us to the end of the notes, is to find all the roots, real and complex, of a given polynomial. So basically the values of x that make y equals 0. Okay, so to check, it says we could solve using factoring techniques, like in 5.3. We can guess and check randomly. Probably not going to do much of that. And then systematically, So the way we're going to attack these is we're going to use our graphing calculator. So we're going to use a combination of technology, and we are going to be using some synthetic substitution, synthetic division, whatever you want to call that. Okay. So on that note, let's go ahead and get started. So it says y equals, we'll go ahead and type that in. I've already gone ahead and typed that in. X to the third minus 2x squared minus 11x plus 12. So I'm going to go ahead and look at my graph. And remember, I'm looking for x-intercepts, and it looks like I have nice, clean x-intercepts here of -3, +1, and +4. We'd want to make sure, looking at our table, all right, so -3 goes to 0. Excuse me, +1 goes to 0, and +4 goes to 0. So basically, it would be that simple. Just to show you how this would shake out, kind of looking at some division there. So we already know, just to be clear, that the solutions are x equals -3, x equals +1, and x equals 4. We can tell just by plugging that into our calculator and looking at the x-intercepts. Okay, just to give you an idea of how that, checking these with substitution or with division would look. So we could take -3 into these coefficients. So 1 for x cubed, -2, -11, and 12. So we bring down the 1, -3 times 1, -3, -2 plus 3, -5. -3 times -5 is 15. Sorry, I'm not sure what happened here. That says -11 though. So that would give us 4. -3 times 4 is -12. All right, so that's the key right there. We get that 0 remainder. That confirms that -3 is a root. Okay, now when we divide, it gets a little bit easier. So now I'm left with this quadratic. So let's divide 1 into that. Don't need the remainder, right? So then we just start again. Bring down your 1. 1 times 1 is 1. Add these, get -4. 1 times -4 is -4. Add those, get another remainder of 0. Now we're left with a kind of a linear factor, which that would just be x minus 4, right? And then if we take 4 into that, bring down your 1. 4 times 1 is 4. And again, we get that remainder of 0. All right, so basically what we did there was we confirmed that all 3 of these were factors, were roots using synthetic division. We didn't really need to do all that, but I wanted to introduce how we can use synthetic division. All right, so let's go ahead and look at B. Okay, B is going to be a little bit trickier. I think I kind of glossed over this, but in A, we knew we should have 3 solutions. And A, we had 3 real solutions, also 3 rational solutions, right? So kind of know what you have there. So like in B, we should have 3 solutions. Okay, so let's go ahead and type it in and see what it looks like. So it is x to the third power minus 4x squared and plus 8. Go ahead and graph it. And it looks like maybe, so that's definitely not going to be a whole number. It looks like maybe 2, but then not 3. So let's just go to the table, make sure 2 goes to 0, and it does. Okay, so that's going to be our starting point. So we already know x equals 2 is part of my solution set, right? And then we're going to use that to kind of get the rest of it, right? So you could think about the rational root theorem here. So it'd be the factors of 8 over 1. Remember that, P over Q. So you'd have like plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8, right? And then when we look back at our graph, we see none of those are really possibilities for this one or this one. So those must be, they're not imaginary numbers, they must be irrational numbers. So that's nice to be able to interpret all that just from what we know about polynomial functions, okay? So we know x equals 2, and again, we're going to use that fact to kind of break this down, okay? So we're going to divide 2 into 1x to the 3, negative 4x to the 2. Remember your 0 for your x, and then 8. Bring down the 1, multiply, add, multiply again, that'd be negative 4. Add again, that's negative 4. And we multiply to get negative 8. And we get that remainder of 0, which we should always get if we're dividing by a factor. Okay, now what we're left with is a quadratic. Okay, so that is x squared minus 2x minus 4. All right, so what can we do with that? Again, we know this appears to have irrational solutions. So we could use either complete the square or we could use the quadratic formula. Okay, so in other words, you're not going to be able to factor it, right? Because it has irrational roots. So let's just go ahead and use the quadratic formula. On the notes, I do both. So if you prefer complete the square, you can look at the notes for that. So we'll go x equals negative b, so negative 2. I'm just going to write as positive 2 plus or minus the square root of, I'm just going to type this in. So b squared, it's just going to be 2 squared minus 4 times a is 1 times c is negative 4. The square root of 36, that's not right. Let's see, b, oh, I did 2x. 2, let's try that again. 2 squared minus 4 times 1 times negative 4. That's going to be 20. That makes more sense because I knew I had irrational roots there. That's why I knew 36 couldn't be it, because that'd be a whole number. Over 2 times a, so just over 2. Square root of 20 is going to break down to, that'd be 4 square roots of 5. And then we'll just reduce, okay? So 2, 2, and 4 can all be divided by 2. So that'll be kind of what I do last. That'd be 1, 1. And that'd be 2. Okay, so in addition to my rational root of positive 2, I also have roots of 1 plus 2 square roots of 5. And 1 minus 2 square roots of 5. Or we could have just said 1 plus or minus 2 square roots of 5. And again, think about what we say about those rational roots, right? They always come in those conjugate pairs like that. Okay, so moving on. I wanted to make sure that I show the ones that I wanted to show. Okay, we wanted to do C, and then I'm going to skip to another example that's not on the notes. And then D and E will just obviously be on the notes. Okay, so we'll start by typing it in. So x to the third plus 4x squared plus 7x plus 28. We look at our graph. So it appears to pass through negative 4. Okay, we'll confirm with our table. Okay, and then we don't really see what happens after that. We could zoom out, but let's just go ahead and work with that negative 4. assuming that it is a 0, and we can see that it is. Okay, so based on what we saw in our calculator, we already know at least one of the 3, right? Should have 3. So we know x equals -4 based on what we saw in our calculator, right? Another way that we could tell it's -4, besides just looking at that, is when we divide, right? Remember this fact too. So if we divide -4 into our 1x cubed, 4x squared, 7x, and 28. So multiply there, we get -4. Add to get 0. Multiply to get 0. Add to get 7. Multiply to get -28. And then that remainder 0. So remember, another way that we can use synthetic, that's why they call it synthetic substitution, right, is what this tells us is, you know, you could say f of -4 is equal to 0. Okay, so that's why we know it's a 0. All right, so now we go from a cubic to a quadratic. Okay, so what we're left with is x squared plus 0x plus 7. Okay, now we could use quadratic formula on this. We could use complete the square. Actually, I don't think we could use complete the square on this one, but we could use quadratic formula. But the easy thing to do here would be just to solve using square roots, right? If we just set that equal to 0, since we don't have that bx term, we're just going to solve algebraically using square roots, right? So isolate the x squared term. We get x squared equals -7. So we get x equals plus or minus the square root of -7. So now we can tell that that function never comes back down or back up to hit the x-axis anywhere else because these are imaginary roots, right? So when we simplify that, that'd be x equals plus or minus I square roots of 7. So those are my other 2 roots, which are imaginary roots, right? So we have 4, we have I times the square root of 7, and we have -I times the square root of 7. 1, 2, 3 roots, 2 of which are complex or imaginary. That's why we didn't see them on the graph. Okay, D and E, I recommend you look at those. But I wanted to show you something different because last year, I remember this was on the test and we never explicitly went over it. So I think it'll be more helpful to make up an example F, which is not worked out in the notes. So this is really the only place you can see this one. All right, so what if we had the equation or the function y equals x to the 4 minus 11x to the 2 minus 26. Okay, so let's go ahead and look at our graph. And we're going to see why this one is a little bit trickier. So x to the 4 minus 11x to the 2 minus 26. Sorry, minus 26. Then we look, and so, all right, so at this point we can see this crosses the x-axis somewhere between -3 and -4, somewhere between +3 and +4, right? But it's not obvious where, and now, like, we can also think about this. Are they rational numbers? So could that be like, could that be like 3 3/4 maybe? Could that be, -3.5 maybe, right? But think about your rational root theorem here. It would be your only possible rational roots would be the factors of 26 over 1, right? So 1, 2, 13, and 26, right? So that's definitely not one, -1, -2, -13, or -26. So at that point, you know that, okay, we got some work. We have our work cut out for us, okay? So we can't really do anything. You're not going to guess and check irrational numbers, okay? In my opinion, right? So you got to have another plan. So far, we've been able to lean on our calculator, but we can't even guess and check with rational roots because we just went through our rational roots, right? When we did P over Q, it would be, 1 over 1 plus or minus 1 over 1 plus or minus 2 over 1 plus or minus 13 and plus or minus 26, right? And again, those definitely aren't any of those, okay? So at this point, you would really you would be left with just factoring, okay? That would be your best bet. Okay, so when you're factoring one like this, that goes from an x to the 4 to an x to the 2 to a minus to a constant, I would really highly encourage you guys to think about the similarities of factoring x squared minus 11x minus 26. Now, if I told you to factor that, most of you would know what to do. You'd say, oh, it starts with x squared, so it's going to be x plus or minus something times x plus or minus something. So then you would think, what's going to multiply to negative 26? Add to 11. I think that'd be negative 13 and positive 2. So minus 13 plus 2. And then you would have it factored, okay? So the only difference with this one, you can also factor this by grouping, but the only difference with this one would be, I'm going to take a shortcut, your first terms start with x squared. Okay, so your binomials start with x squared and x squared. And then it still, ends with negative 13 and positive 2. All right, so, with that green one up there that I made up that was similar to this, our roots would be 13 and negative 2. Okay, here it's not quite that simple, but it's close. So if we set that equal to 0, because we don't have that bx term, we would get x squared equals 13. And so x equals plus or minus the square root of 13. Now you could punch in what is the square root of 13, but just think about it, right? So that's between the square root of 9, which is 3, and the square root of 16, which is 4. So it's somewhere between 3 and 4, which seems to match up with what we see on our graph. This is between positive 3 and positive 4. This is between negative 3 and negative 4, right? Which would match up with this, okay? And then our other factor, it's not a linear factor, but it's a pretty easily solvable factor. If we go x squared plus 2 equals 0, that would get me to x squared equals negative 2. And x equals plus or minus the square root of negative 2. And so x equals plus or minus 2i. Or sorry, I square roots of 2. Let me let that pop up real quick. I square roots of 2. All right, so there you see all 4 roots. Okay, so I'd be fine with you listing them out this way. If you wanted to list them out to where it looks more like 4, you could say x equals the square root of 13, negative square root of 13. And again, going back to our previous lessons, these irrational roots always come in conjugate pairs, just like that. And so do the imaginary roots, right? So if you have I square roots of 2, you must also have negative I square roots of 2. So that would just be another way you could write out those 4 roots. Okay, so like I say, this is the last lesson, the last big lesson. I might give you a bonus question out of 5, 7, but this is going to be the last thing you're really tested on and held accountable for. You guys, as always, let me know if you have any questions. Thanks for all your hard work and hope this helps.